can we talk about the Big Bang a little bit?
Sure. Yeah, yeah. Uh-huh.
So like the entirety of it, the universe
Yeah,
was very small.
right. But it was not a point,
It was not a
okay?
point.
Because if we live in what's called a closed universe now, a sphere or the three-dimensional version of that would be a hypersphere,
Mhm.
you know, then regardless of how far back in time you go, it was always that topological shape. You can't turn a point suddenly into a shell, okay? It always had to be a shell.
Yeah.
So when people say, well, the universe started out as a point, that's being kind of flippant, kind of glib. It didn't really. It just started out at a very high density. And we don't know actually whether it was finite or infinite. I think personally that it was finite at the time, but it expanded very, very quickly. Indeed, if it exponentiated and continued in some places to exponentiate, then it could in fact be infinite right now. And most cosmologists think that it is infinite.
Wait, yeah, sorry. What infinite? Which dimension? Mass?
Infinite in
Size?
space, infinite in space. And by that, I mean that if you were trying to
There's no boundary? Okay.
use light to measure its size, you'd never be able to measure its size because it would always be bigger than the distance light can travel. That's what you get in a universe that's accelerating in its expansion.
Okay, but if a thing was a hypersphere, it's very small, not a point.
Yeah.
How can that thing be infinite?
Well, it expands exponentially. That's what the inflation theory is all about. Indeed, at your home institution, Alan Guth is one of the originators of the whole inflationary universe idea, along with Andrei Linde at Stanford University here in the Bay Area. And others, Alexei Starobinsky and others had similar sorts of ideas. But in an exponentially expanding universe, if you actually try to make this measurement, you send light out to try to see it curve back around and hit you in the back of the head. If it's an exponentially expanding universe, the amount of space remaining to be traversed is always a bigger and bigger quantity. So you'll never get there from here. You'll never reach the back of your head. So observationally or operationally, it can be thought of as being infinite.
That's one of the best definitions of infinity, by the way.
What's that?
That's one of the best sort of physical manifestations of infinity.
Yeah, because you have to ask, how would you actually measure it? Yeah. Now, I sometimes say to my cosmology theoretical friends, well, if I were God and I were outside this whole thing and I took a godlike slice in time, wouldn't it be finite no matter how big it is? And they object and they say, Alex, you can't be outside and take a godlike slice of time,
because there's nothing outside.
Well, I'm not, or also, what slice of time you're taking depends on your motion. And that's true even in special relativity, that slices of time get tilted in a sense if you're moving quickly. The axes, X and T, actually become tilted, not perpendicular to one another.
Got it.
And, you can look at Brian Greene's books and lectures and other things where he imagines taking a loaf of bread and slicing it in units of time as you progress forward. But then if you're zipping along relative to that loaf of bread, the slices of time actually become tilted. And so it's not even clear what slices of time mean. But I'm an observational astronomer. I know which end of the telescope to look through. And the way I understand the infinity is, as I just told you, that operationally or observationally, there'd be no way of seeing that it's a finite universe, of measuring a finite universe. And so in that sense, it's infinite, even if it started out as a finite little dot. Well, not a dot, I'm sorry, a finite little hypersphere.